In this video, we're going to be talking about permutations and combinations, or different counting methods. A permutation, and the notation we use for that is P and K like this, counts the number of ways n distinct objects can be arranged K at a time where the order of the objects is important. And this is the formula we have for this. I'll go over exactly what everything means in a minute. Key terms that a problem is going to be a permutation problem. If you see the words arrange, order, line up, permute, or it's talking about situations where distinct roles or jobs are being assigned, it's probably a permutation problem. Now, the way this formula works is this is n factorial divided by n minus k factorial. So the way a factorial works is if we have 3 factorial, that would be 3 times 2 times 1, which is equal to 6. 4 factorial would be 4 times 3 times 2 times 1, which is equal to 24, and so on. Let's look at an example. Suppose we have a collection of 5 different films. We'll call them A, B, C, D, and E. And we want to know how many ways can we arrange 3 of them on a shelf. The word arrange tells us order is important, or order matters. So if we wanted to see how many different ways we could do this, one possibility is to list them all out by hand. And here are all of them listed out by hand. So we could do this and see that there's 60 different arrangements, but it can take a long time to list things out by hand. So we're better off using the formula. So the formula over here would be a permutation of, we have 5 objects and we're permuting 3 of them. So this would be 5 factorial divided by 5 minus 3 factorial, which is 5 factorial over 2 factorial. That's 5 times 4 times 3 times 2 times 1 divided by 2 times 1. These are common factors that divide out. 5 times 4 times 3 is equal to 60. Now we'll talk about combinations. A combination denoted C and K. Other ways you also might see this written are like this. NK like this, which would be read N choose K, or NCK like this. Counts the number of ways n different objects can be put into groups of size K. The order of the objects does not matter. So some key terms that'll let you know you have a combination problem instead of a permutation problem. Words like choose, select, group, committee, or situations where order is not important. Generally food questions unless there's something else to indicate that order does matter. So generally these key terms work, but you do need to pay attention to context. And the formula we have for a combination of k out of n objects is n factorial divided by n minus k factorial times k factorial. Again, suppose we have a collection of 5 different films. We're calling them A, B, C, D, and E. How many ways can we choose a group of 3 movies to watch? Here we can use our combination formula. And there are some common factors that we can cancel out, so we end up being left with 5 times 4 over 2. 20 over 2, which is 10. And the key term that signaled that order doesn't matter in this problem is choosing a group of 3 to watch. They didn't say the order you're watching them in makes a difference. You just care about what 3 movies you're watching. And now one thing we might notice is when we did the combination of 3 out of 5 objects, the answer we got was a lot smaller. 10 is a lot smaller than 60. And let's say we want to know, well, why is that? If we go back to all the possible arrangements that we have listed out over here, in a combination, a couple of them are repeated or considered duplicates of each other. So ABC, BAC, CAB, these ones that are circled in blue are all considered equivalent in a combination. Because here, in a combination, you just care about who's in what group. So for a combination, we just care that we have movies A, B, and C in the group. If we're talking about a permutation, these 6 things are all different arrangements because you care about the order. When you just care about what's in the group and not what the arrangement is, you're going to have fewer outcomes. And thankfully, you can also do combinations and permutations on your TI-83. I am going to update the calculator information sheet or the calculator tutorial sheet in Google Classroom with more details and pictures on how this works. Let's look at another example now. I would suggest pausing the video here, try to work it out on your own, then hit play to see me go through the answer. Suppose a bakery has 12 different flavors of cupcakes. how many ways can A, you choose a group of 3 different flavors. So when they say choose a group here, that means order doesn't matter, and that we should use a combination. So we only care about what 3 different flavors are in the group. We don't care about how they're arranged or ordered or placed or anything like that. We would use our combination formula here. And once we evaluate this, we end up getting 220. For part B, we want to know how many ways can 3 different flavors be arranged in a store window display. So we see the key term arranged, and also since they're talking about a display, these are both words that signal order is important and that we should use a permutation. So we can plug this all into our permutation formula. And here we end up getting 1,320. Now you also could have opted to solve this using the counting principle or the product principle. So if we wanted to solve it that way, we know that we have 3 spots in the window display, and because we want to use 3 different flavors, we're not allowed to repeat flavors. So you have 12 choices for the first spot, you have 11 choices for the second, and then 10 choices for the third. And then 12 times 11 times 10 is also equal to 1,320. So you can use the product principle for permutation problems, but you can't use the product principle for combination problems. Let's see one more example. Again, I would suggest pausing the video, try to figure it out on your own, then hit play to see me go through the answer. Suppose Alucard has a collection of 20 different warning signs. How many ways can he choose to arrange 2 of them in front of his house? Again, we see the word arrange. So this means that we're dealing with a permutation because order is important. So we could plug this into our permutation formula. And we end up getting 380. We also could have opted to solve this using the product principle. We have 2 spots for the signs in front of the house. There's 20 ways you could place the first sign. Then once you've placed one sign, you can't use it again unless you have some sort of a cloning machine, but the problem will specify if you do have a cloning machine or not. And then you only have 19 possibilities left for the second sign you could use. You multiply 20 by 19, we end up with 380 again. So now just to summarize some of this. For permutation, order matters, repetition of objects is not allowed. For combination problems, order does not matter, repetition of objects is not allowed. For product principle problems, order matters, and then repetition of objects can be allowed or not allowed. So what permutations, combinations have in common is you're not allowed to repeat objects, and what permutations and the product principle have in common is that order matters for both of them.